Welcome to EFI Advanced Part 21. In this video, we're going to be looking at how to work with a variable lift camshaft design and what we're going to need to know in our tuning process. We have a lot to learn, so let's get started. Okay, so let's get this video started by talking about our variable valve lift style camshaft design. Now, this is going to be most notably found in the Honda line of engines with a function called VTEC. Now, it's going to allow us to have essentially two different profiles of a camshaft on one camshaft. So we're going to have a low lobe profile that's going to idle and drive around in normal driving conditions. That's going to have a relatively low overlap, and it's going to be a relatively mild profile. So we're going to find that idle and our cruising are going to be nice and smooth. Now, we're also going to have a race profile on that same camshaft design that's going to have a much greater overlap, much greater duration, and much more lift. And that's going to be actuated or turned on at higher RPM levels. Now, this is going to give us the best of both worlds because we're going to be able to have a cam that's going to have that low overlap, nice smooth idle, and then switch over to a race profile where we can really turn on that power and completely change the volumetric efficiency of your engine. Now, let's just look at how this is mechanically going to work so we have a better idea. Now, if we look here, we can see that we're going to have three different rocker arms and we're going to have a camshaft. Now, if you note on the camshaft, it's going to have two sets of profiles. You're going to see one mild set or lower set, and we're going to have one much greater or much larger lobe on the camshaft. Now, we can see that as the camshaft is going to spin around, the two outer rocker arms here are going to ride on these two smaller lobes of the cam. Those are going to actuate open the valve under normal driving conditions. So at idle and our part throttle operation, those are going to be what's controlling the engine and letting the airflow into the engine. Now, once we switch on the VTEC function, this slider pin is going to slide into all of the rocker arms. It's going to lock them together, and it's going to force that middle rocker to ride on the largest profile in the camshaft. So this rocker this slider pin is going to actuate and slide across once there's oil pressure that's going to be pushing it across. So that's going to be what we control from an oil control solenoid that's on the engine. So when we turn it on, it's going to increase the oil pressure to this rocker assembly, slide that pin over, lock it into that high cam profile. Now, when it's running on that high cam profile, we're going to have a completely different amount of airflow coming in the engine because, again, the duration, the lift, the overlap, they're all going to change. So we're going to have a completely different engine, how it performs. So we're going to have different fuel and ignition demands as well once that changes over. So now that we understand how this mechanically works and the idea of having two different profiles, let's move into the tuning process and what we need to know in order to tune a variable valve lift system properly. Okay, so now that we understand how our variable valve lift timing system works, mechanically let's move into the virtual or programming side of things so we understand how we're going to be controlling it and how we're going to be actually tuning with this system. Now, because we have two different sets of distinct profiles on our camshaft, we're going to have two different sets or deliveries of air mass coming in our engine, and therefore we're going to have a completely different amount of fuel mass that has to be delivered. And because the overlap is going to change and the duration is going to change on our high cam profile, that's going to be changing the dynamic compression ratio and therefore changing the timing demand or spark timing on our same engine. So we're going to have to characterize this somehow. So let's look at how Honda went ahead and controlled or designed this system to work virtually. So if we look at a Honda S300, this is going to be based on the older Honda B, D, or H series engines, and this is going to allow us to go ahead and tune those engines with a Honda computer. Now, Honda designed the virtual side of things here based on a low and a high cam profile for the fuel and ignition timing tables. They knew that there's going to be completely different sets of air mass coming into our engine with the different cam profile, and the spark timing is going to change because our dynamic compression ratio is going to change. So they knew they needed to characterize it, and the best way to do that is to have completely separate fuel and ignition timing maps depending on which profile of the cam we're running on. So if we look here, we can see that we have our low cam fuel map, and then we can see here that we have our high cam fuel map. Now we can just look at the values in the table, and this is going to be a time-based model, so it's not going to be volumetric efficiency based. The values in the table are relatively arbitrary. We just need to know that if we move them up, that increases injector pulse width. If we move them down, that decreases the injector pulse width. So looking back at the table, we can see that the low cam value and the high cam value are relatively a big jump between these two tables. So we can see there might be a 20 to 50% difference in the values in the table, because there's going to be that much greater demand for our air mass coming in our engine on the high cam table. Now that's going to be substantial because we can go ahead and control the fuel delivery just for that specific high cam event. So if we ride on our low cam and switch to the high cam, we're not going to have to worry about blending one gigantic fuel table. We're just simply going to switch over to this table and be able to hit that exact fuel delivery that we want. Now on the same side of things, we have a low cam ignition timing table and a high cam ignition timing table. And if we look at the values in the table here at something like wide open throttle, we can see the values on the low cam are about 23 to 24 degrees. And looking at the same wide open throttle area on our high cam, we can see they're between 28 to 31 degrees. That's a large difference in ignition timing, and that's because that intake valve closing point is changed on that high cam, and that's going to change our dynamic compression and lower it, and therefore we're going to be able to increase our ignition timing, and that's going to allow us to do that safely because of that profile switch. So when we switch to the high cam, generally speaking, we're going to have a bit more ignition timing because our dynamic compression ratio decreases. Now that we know how Honda went ahead and controlled the variable valve lift system, or the VTEC system, let's look at how we're going to do it on a standalone. Now, most standalones are not going to have two sets of tables. We're going to have one main fuel table and one main ignition table. So we're going to have to go ahead and characterize this variable valve lift when it switches over, and have the fuel table built so that it has enough fuel there, and then we're going to be able to make that switch over point and not have any stumbling where it's rich or lean. So if we go ahead and just tune the low cam, we're going to find our fuel table is going to look like this. Now this represents the volumetric efficiency look of our low cam air mass model coming into our engine. Now if we look here, this is going to represent when we turn on that high cam, and we're going to have a completely different look to this fuel table. It's going to be much higher values of volumetric efficiency, and that's because our air mass is going to be substantially increased when that cam switches over to the high cam profile. And we can see this nice visual representation of the difference of fuel demand between the low cam locked in and then the high cam turned on. So we're going to have that kind of drastic jump in our fuel table. Now our spark table is going to have the same kind of concept. Typically speaking, we're going to have our variable valve lift engaging anywhere from 4,000 to 6,000 RPM. So on our low cam, we might find if we just make a pull on low cam, our ignition timing values are relatively low. Something like 21 to 22 degrees, and we switch on our high cam, wherever that point may be, we're going to find that our values are going to, in this single ignition timing table, are going to ramp up with engine RPM because we have that dynamic compression ratio change. It decreases, and we're going to be able to run more ignition timing. So we're going to have a table that kind of looks like this. So there's going to be two different kind of ignition profiles, tables that we'd essentially run. We're going to have to roll them into one to have one table, and same with the fuel tables. We're going to have to roll everything into one, and then we're going to have to go through and make sure when we switch the cam on or off that we don't have a rich or a lean spot. And if we do, we might have to go in and tweak the table. So this isn't going to be the most ideal way to control it, but we can do it with enough patience and going through the table and checking the switch from the low cam to the high cam and back from the high cam to the low cam, and we can characterize it and make the engine run properly with this kind of system. Okay, so now that we understand that there's going to be a low and high cam fuel and ignition timing table, let's go through the calibration process so we really understand what we're going to need to do when we're tuning this variable valve lift system. So first thing is going to be, we're going to turn off the variable valve lift completely. We're going to go in, we're going to tune our low cam fuel and ignition timing tables, or if we have that single fuel and ignition map, we're going to go ahead and tune that and get the characteristic volumetric efficiency shape and make sure that table is set up as best as we can. So we're going to go through the same process or techniques that we found in these other videos for setting up our main or low cam fuel and ignition timing table. Then we're going to switch on the variable valve lift system at a very low point, something like 3,000 RPM. We're going to go through that same calibration process, sweeping through the part throttle areas, going into the full throttle areas, setting up our fuel tables, going and setting up our ignition timing, trying to find our maximum brake torque timing, and then mapping out that the high cam fuel and ignition timing table. Now, once we've done that, we've characterized the engine for the completely different amount of air mass entering our engine. So the fuel is going to be correct and the spark is going to be correct. Now the next point is going to be figuring out where to set that variable valve lift point. Now we can't just choose where we want it to set it. We actually have to look at what is going to work with the airflow that's coming in and out of the engine. So depending on the intake and exhaust system, we're going to have a point that may be different from one engine to another, even if we're using the same camshaft profile. And that's going to be something to always keep in mind. Just because you thought or found that a particular camshaft design runs at, say, 5,000 RPM on one engine, it may have to be at 6,000 RPM on the other, depending again on what the combination of parts we have on the engine. So we're going to go and use this variable valve lift point technique every time we tune. After we've done the main low cam fuel and timing tables and done the high cam, we're going to go ahead and look at where the two torque curves cross. So again, we locked that low cam in, we locked the high cam in. We're going to look at where the two torque curves cross. That point where they cross is going to be right around the optimal point for VTEC to engage now, or the variable valve lift to engage. So we're going to go and set our valve lift point there. Then we're going to go and make a pull and see exactly how the torque curve looks. Our goal is to have the smoothest and broadest torque curve possible with this dual lift system. So we're going to go ahead and do a pull with it locked in and see what it looks like. And then we're going to go and move that point several hundred RPMs before and after to make sure that there isn't some more to gain. Now, sometimes if we have a very efficient intake and exhaust system, we can move that point a bit lower than we found that intersection point and actually pick up a bit more torque and horsepower. So it's always good to go ahead and try and do that. Now, we want to verify again, once we lock that activation point in, we want to make sure that our fuel is staying consistent air fuel, and we're making sure that the switch from our low cam to high cam is going to be seamless on the ignition timing table, and we don't have a very pronounced switch over, and our timing doesn't create like a bogging effect going from the low to high cam. So we're going to make sure all that's smooth and try that experimentation with that engagement point and see if we have anything else to gain. And once we've done that, then we've successfully tuned a variable valve lift timing system. And it's relatively simple. Now, the one kind of pointer that I can give you that's going to be very key is we don't want the activation point to be turning on all the time. So if we're, for example, setting our VTEC engagement point or our variable valve lift engagement point at something like 3,600 RPM, we don't want to be driving down the road and being on the high cam, on the high profile lift operation, because that's going to consume more fuel. Because we're allowing more air mass in the engine, we have to deliver more fuel mass. Our economy is going to go down a lot, and we want to avoid that. So in addition to programming our activation point, we're going to have to program some other factors, such as the engine load turns on and the throttle, that percentage of the throttle angle that we want the lift system to turn on at. So we're going to have a combination between the RPM point that we found that was optimal, then a throttle position that we find that's going to be optimal, and the engine load. So we might find something like -2 psi of vacuum might be appropriate, and something like 40% throttle if we have something that has a very low activation point, such as 3,500 RPM to 4,000 RPM, and that we can avoid getting on that high cam, just simply cruising down the highway or cruising the road, and we can get better fuel economy, and the car will drive a bit smoother like this. Now we have to go ahead and then test it in those conditions and make sure once we get on the throttle and back off that it's going to have a smooth transition on and off. Now the other thing that we need to keep in mind is that there is going to be a hysteresis function in the engine RPM. So if we have the on point at, say, something like 3,600 RPM, we have to have the off point at something like 3,400 RPM. We don't want to have the on and off point at 3,600 RPM, because if it turns the solenoid on and off at that same point, we might find if we're riding at 3,600, it might turn off and on and off and on, and we create a lurching or a surging effect because we're switching the cam off and on. It's going to be hard on the engine mechanically, but it's going to create a very abrupt feeling when you drive. So we want to have this hysteresis function where we have a window of where it can turn on and off, so there's adequate time for it to turn on and off and not stress the engine and not give you that abrupt switchover feel. Okay, so for the last part of this video, I want to give you guys some tips while you're tuning your variable valve lift, some things that you might run into that you need to be aware of that's going to save you a lot of time and headaches. So the first thing is, just because we're switching on to the high cam does not mean that we're going to make more power. Now, if we have a very restrictive exhaust system, or we have a catalytic converter that's bricked up, that doesn't have or not allowing the exhaust gas to get through it, we're going to find that in this situation, we're going to have that exhaust scavenging effect when the cam profile switches over. We're going to have the increased overlap. We're going to find that we're going to have the opposite effect of the scavenging. We're going to be pushing that exhaust pressure back into our combustion, and it's going to raise our temperature. It's going to make the engine more knock prone, and it's going to dilute the amount of air mass that's coming in the cylinder and lose power. So when we switch over with a very restrictive exhaust, we're going to find that it bogs out and it loses power. Now, it may be so bad that you can't even turn on your high cam of your variable valve lift. Now, you're going to know this when you do the low profile tuning and then you switch over in the cam and you do the high profile tuning. You're going to find that when you look at the dyno graph, your high cam may be making less power than your low cam. And you're probably going to be thinking, what the heck is going on here? Well, this is going to be because you have some kind of major exhaust restriction. So that's going to be the first thing to note. Now, the second thing is, if you're not on a dyno and you're tuning your variable lift system and you're tuning your fuel tables, you always want to look at the comparison between the values. Now, if you look at the low cam fuel and then you look at the high cam fuel, you can get an idea of how much of a difference of the values in the table are going to be. So if you see something like a 20% difference in our fuel demand, you can expect that you're making a bunch more power. But if you look at the tables and the values are kind of similar, that means that the engine's really not making any more power when you switch over to the high cam, and that's because you have some kind of a restriction. So that's another kind of checks and balances while you're doing your tuning process. You should always see the values be quite a bit higher, usually at least 20 to 50% higher on your high cam fuel map than you do on your low cam. That's going to indicate that that engine is making good power. Now, another thing to keep in mind here is if you're doing your tuning for your variable valve lift on the road, you're not using a chassis dyno, you can still tune it properly by paying attention to this very minor detail here. Now, when we do our low cam tuning at full throttle, we're going to go ahead and we're going to set our table so we get the desired air fuel that we want, and then we're going to go into our high cam and we're going to do the same thing. We're going to set the table up, and then when we go back and we look at the values in the table, we're going to see where the value is the highest on the low cam and the value is the lowest on the high cam table. Now, at that point, we can typically look at the values and they should be relatively close to each other because our fuel demand at that point is going to be very similar, because our torque output of our engine is going to be very similar. So if we were able to take this low cam table and this high cam fuel table and we looked at the torque curves plotted on a dyno graph, we're going to find that point where if we have the peak in our fuel table value on the low cam is going to be the peak of our torque, and then on the high cam we're going to find that same peak or the same spot where the torque is relatively low or flat, and we're going to see that same point on the table. We're going to match those values up or get as close as possible, and that's going to give us a very good starting point for the engagement point in setting the VTEC function in our programming. So that's just something that you can pay attention to and really know as a checks and balances, or at least gave you a good starting point for the activation point. Then you're going to have to go ahead and drive it and see if it feels good, but at least you're going to have something that's going to get you within that 5 or 10% range of where that point needs to be, just by paying attention to our fuel delivery and our fuel maps. Now, another thing to keep in mind is if we're tuning a forced induction engine with this VTEC function, and it's a turbocharged engine, we can manipulate this variable valve timing point and change it so that we can aid in the turbocharger spool. Now, if we can get onto that high cam sooner, we're going to be moving more air mass in our engine, and therefore we're going to have more exhaust air mass in our exhaust manifold. That's going to build a bit more pressure, and it's going to spin the turbo faster. We are going to find that same optimal point where we're going to be moving our VTEC point down and trying to figure out where the lowest we can run it. And we're going to find that the engine starts to actually bog out and not really want to make any more power or spool the turbo faster. And that's because we're going to have that backing up effect during the overlap period where we're going to have the exhaust pressure pushing back in the chamber. We're going to have the opposite reversion effect, and we want to avoid that. So there is going to be a sweet spot for finding the VTEC point on a turbocharged engine, and we can do that same process where we do the low cam in boost and then do the high cam in boost and figure out where that point is. But as we increase in boost pressure, we might find that that VTEC point can go lower and lower, and that's because that exhaust pressure is going to increase and spin our turbo faster. We're going to get into boost faster. It's going to make it a little bit more efficient. So if we're tuning an engine, say on 6 psi, we might find that the VTEC point is at 5,000. And then if we tune that same engine and we turn up the boost to something like 20 psi, we might find that we can lower that VTEC engagement point to something like 4,500 still be smooth and aid the turbocharger in spooling faster. And that's just going to be because of that scavenging enhancement effect as we're pushing more intake or air mass in and having more air mass come out and spool that turbocharger faster. So that's something to be mindful of when you're tuning a turbocharged engine with this VTEC function.